All right, so our last video on sequences is going to be a little bit more theoretical. Instead of evaluating limits of sequences by using all of our old limit techniques, which is a little bit more of a computational process, you often have to do some algebra to evaluate the limits, but there's not a whole lot of work beyond that. We're actually going to use a couple of important theorems to help us determine whether a sequence has a limit or not. All right, and before we can actually use these theorems, there are a couple of terms you're going to need to know. So the first thing is, what does it mean for a sequence to be bounded? We say the sequence is bounded above if all of the terms in the sequence are less than or equal to some number, capital M, and we would call this an upper bound for the sequence. All right, so the idea is if you could lay out all the numbers in the sequence and none of them are going to be bigger than a particular number, then we would call that number an upper bound, and we say that the sequence is bounded above. Similarly, you can have a sequence that is bounded below, and as you might guess, that just means all of the terms in the sequence are bigger than some number. We'll call that little m, and that is what is known as a lower bound. And a sequence is going to be called bounded if it has both a lower and upper bound. All right, so just to look at a quick example, think about the sequence 2 to the n, where the terms are 1, 2, 4, 8, 16, and so on. This we would say this sequence has it was certainly bounded below the lower bound is, well, one lower bound would be 1, right? All the terms of the sequence are bigger than 1, but it has no upper bound. Right? Doesn't matter what number you pick, eventually the terms in the sequence are going to exceed it. Eventually they get bigger than 1,000, and eventually they get bigger than 1,000,000, eventually they get bigger than anything you could imagine. All right, so this sequence is not bounded, but it is bounded below. On the other hand, if we think about something like an equals 1/2 to the n, you'll notice I keep coming back to these examples because they are particularly important in the study of series, which we'll get to next time. This sequence has terms like 1, 1/2, 1/4, 1/8, 1/16, and so on. And this sequence has an upper bound for sure. The upper bound is definitely 1, right? None of these terms in the sequence are bigger than 1. Does it have a lower bound? Well, notice, certainly all of these terms are going to be positive, right? There's no way we can raise 1/2 to an integer power and get something negative. So it would be reasonable to say that -1 is a lower bound. But most often what we're interested in is what's called the greatest lower bound, or the least upper bound. In this case, the largest number that would still be a lower bound is 0. Right? All of these numbers are going to be greater than 0, and so we would say that yes, this is a bounded sequence. All right? So 1/2 to the n is bounded, 2 to the n is not. Now, why do we care if a sequence is bounded? Well, knowing that a sequence is bounded gives us a clue about convergence, because you can prove the following theorem. If a sequence converges, meaning if it has a limit, then the sequence is bounded. All right, so every convergent sequence, every sequence that has a limit must be bounded. And you can think of that, you can make sense of that as the following way. If the terms in the sequence are approaching some number, so let's make a little explanation here. Suppose we have some sequence and maybe it bounces around a little bit, but it does converge to something, right? Meaning I can draw a little band around what I think it's approaching, and eventually all the terms in the sequence are going to be within that band. And as small as I make that band, eventually I can accomplish this goal. All right. So suppose it is actually convergent. Well, that means that beyond some point, it looks like maybe right here, all of the terms are close to the limit. So if I call this limit L, in this case it looks like maybe that's at the x-axis, so maybe that's 0. All of the terms are going to become arbitrarily close to L. And so we could say, for example, that all of the terms are definitely going to be eventually between L plus 1 and L minus 1 for sufficiently large n. If I go far enough in my sequence, they're all going to have to be relatively close. All right, so if the sequence converges, we know at least at the tail end that the terms in the sequence are bounded between L plus 1 and L minus 1. But what about the early terms in the sequence? What about the ones right at the beginning? Well, notice that there's only a finite number of those. And so if we were to take the largest term at the beginning, which looks like that one, and the smallest term at the beginning, well, those are potential candidates for a lower bound and an upper bound. And therefore, we know that the terms at the end of the sequence are bounded. We know that the terms at the beginning of the sequence are bounded, so the sequence itself must be bounded. Okay, so to summarize, the theorem says any convergent sequence has to be bounded. Now, notice what it does not say. It does not say that every bounded sequence converges. In fact, you can convince yourself that that's not true. That's a false statement. It's not true to say every bounded sequence converges. And an example of that would be the sequence an equals -1 to the n. Remember that the terms in this one, which we wrote down earlier, were just 1, -1, 1, -1, 1, -1, and so on. Well, this is a sequence that is bounded, right? The largest this terms ever get is 1, and the smallest they ever get is -1. So certainly there is an upper bound of 1 and a lower bound of -1. But does it converge? Well, no, right? You see that the terms are alternating between two values, but they're not really approaching any particular number. So this statement is false. It is not true that we can just flip the order there and say that bounded sequences converge. Convergent sequences are bounded. Bounded sequences may or may not converge. All right, so that's the first set of terms. We need to know what it means for a sequence to be bounded. What about sequences being increasing or decreasing? That's another important characteristic. So we can say that a sequence is increasing if the next term, which I'll call an plus 1, is always at least as big, if not bigger, than an. And we could say the sequence is decreasing if, well, the next term is smaller than the current term. All right, and we can say that a sequence that is either of those is called monotonic. Mono meaning one, and tonic is referring to has basically just one trend. It's either always going up or it's always going down. Okay, so sequence can be increasing, it could be decreasing, it could be monotonic. And so examples of those would be, well, 2 to the n. That was just 1, 2, 4, 8, and so on. That is increasing. On the other hand, 1/2 to the n, which was 1, 1/2, 1/4, 1/8, and so on. That's decreasing. We could also look at, say, -1/2 to the n, which is 1, -1/2, 1/4, -1/8, and so on. And this one is actually neither of the two. It neither increases all the time or decreases because it's bouncing back and forth. So you don't necessarily have to be increasing or decreasing. You could be neither of the two. All right, quick hint for you. If an is equal to f of n and f prime of n is greater than or equal to 0, or f prime of x rather, since often it doesn't really make sense to talk about derivatives of a function that only takes in integer values, but if we allow it to take in continuous values, then we can take derivatives. Well, what would that mean? Well, if the derivative is positive, then the function is always getting bigger and bigger and bigger, so we could then conclude that an is increasing. And similarly, if we change this to f prime of x is less than or equal to 0, then we would say that an is decreasing. So if you want to tell if a sequence is increasing or decreasing, one technique that you have at your disposal is you can take the derivative of the function that allows you to calculate values of terms in the sequence. And once you look at the sign of that derivative, is it positive or is it negative? If it's consistently always greater than 0, we know it's increasing. And if it's always less than 0, it's decreasing. All right. So why do we care about all this? Why is all this stuff important? Why does it matter if a sequence is bounded or increasing or decreasing? Well, that brings us to the last theorem. And that is a sequence that is monotonic and bounded must converge. All right, so we just argued that it's not enough to say that a sequence is bounded to conclude that it converges. We looked at -1 to the n, and we saw that that one did not converge. But if we add the stipulation that we must be looking at a sequence that is monotonic, if it's monotonic again and bounded, then we conclude that it converges. And that's a very powerful result. That's going to help us be able to evaluate the limits of some relatively complicated sequences where maybe the formula for an is a little bit hard to write down or hard to work with. But if we can show that a sequence is monotonic, meaning it's always increasing, and it's always bounded, then we can conclude that it's a convergent one. So I won't go through all the details of this, but an example of one such sequence is the sequence that looks like this. An plus 1 is equal to the square root of 2 times an, meaning each term is the root of 2 times the previous one. And if you write down terms in the sequence, let's suppose that a0 is just root 2, or how about 2? a0 is 2. Then a1 would be, no, let's make that square root of 2. All right, so a1 would be root of 2 times root 2. And a2 would be root of 2 times the previous one, which is root 2 of root 2. And you'll notice as we go on, we just get more radicals that pop up. And the question is, what does that sequence approach? Does it actually have a limit? And I notice I haven't written down a nice formula for you for what the actual terms in that sequence are in the traditional way. Usually we've described a sequence by writing an equals some function of n, whereas here we've actually written down an plus 1 in terms of the previous term. So that's going to limit some of the techniques that we have at our disposal for actually evaluating this limit. But here's the claim. And you might want to read through the chapter 10.1 to get some of the details of this. The first claim is that this sequence is bounded. It's bounded. All of the terms in the sequence, you can show that they are less than 2 and greater than or equal to root 2. All right, it takes a little bit of thought to convince yourself that that's true, but it is indeed true. And the second is this sequence is monotonic. Oops. it's actually increasing. And you can check that if you actually compute the terms in the sequence as decimals. Notice that each term is, well, the first term was root 2. The second one is root 2 times some number that's a little bigger than 1, so it's got to be a little bigger than root 2. And the next one is root 2 times some number that's still bigger than that. So each time the sequence has to grow. And so this is a bounded sequence. It's a monotonic sequence, and therefore it must converge. All right, so note that that doesn't tell us what it converges to. It just tells us that it must converge. But there are some clever ways of actually finding the limits of sequences like this one. In this case, you can actually solve an equation that eventually, if the sequence converges, that means the next term and the current term must be the same. And so we could try to solve an equation like this. The next term and the current term, we'll just call them both a. And if we can solve for the value of a that works, well, we will be in good shape. And notice that if you square both sides, we'll have a squared equals 2a, or we could rewrite that as a squared minus 2a equals 0, or a times a minus 2 equals 0. And in that case, notice a equals 0 and a equals 2. Would both satisfy that? Well, it's pretty clear that 0 can't be the answer, because all of the terms in the sequence are between root 2 and 2. So you can't approach 0 if you never get anywhere close to 0. Root 2 is around 1.4. We don't have any terms smaller than that. But 2 is very plausible, and it turns out that is actually what these numbers are approaching. Okay, so this is a tricky problem. I wouldn't necessarily expect you to figure this one out for yourself, but we will reference this theorem from time to time, especially when we're talking about series. And so it's good to remember the central message that if a sequence is monotonic, it's either increasing or decreasing, and it's bounded, meaning it has some upper limit and lower limit that never gets above the upper limit or below the lower limit, then the sequence must converge. All right, that's it for this unit. We'll talk about series next time.